Good morning. Thank you so much for giving an opportunity to present my work here. I'm very happy. We saw a very good work by Dr. Shah explaining about the wearable energy harvesting system for wearable electronics. We are very happy about this work because we are doing some work towards in that area also. Uh, I'm presenting one of the work one of my student did Guanbo, especially in the terms of energy harvester by using a triboelectric nanoenergy harvesting, how to optimize that triboelectric energy harvesting by controlling the dielectric permittivity of the material and the thickness of the substrate. I am working at University of Glasgow, one of the research group called the Bendable Electronics and Sensing Technology Group. We are mainly focusing on flexible electronics for various applications, including robotics or wearable systems, tactile sensor, wearable sensors for healthcare applications, water quality monitoring. Uh, in this work, wearable sensors, we know that wearable sensors require a lot of power, as you mentioned in the previous presentation also. So the power mainly be used by batteries or some other energy storage or energy generators applications. So in this talk, I will discuss with you some of the why we are doing this triboelectric energy harvester for a particular applications and the basic experiment. This is mainly I didn't explain here any experimental results, mainly the simulation results which I am going to discuss with you, and the some of the results and conclusion and feature. As you know, in wearable sensors, uh, presently we have many wearable sensors, including tactile sensors, sweat monitoring sensors. All these type of sensors require power. But due to the advantage of nanomaterials in material technology or device fabrication, the sensors are operating nano power range or microwatt power range. So sensors required a power range, and also the wearable sensors required an electronics to operate those. So mainly we are using energy generator like piezoelectric energy harvesting or solar cell or from other energy like thermoelectric and everything. But one of the major problem of the present means the wearable application is that how can be a flexible energy harvester, a suitable power applied to flexible from the for a wearable system from a flexible energy generator. So and also this energy generator requires a storage which is mainly using by batteries, or nowadays we are using supercapacitor also. I can show you some of the work which recently which I published in one of the nanogenerators paper. In this one, what I did is that I fabricated a supercapacitor based on a graphene form, and that energy to charge that supercapacitor, I used a solar cell, and that stored energy used for a pH sensor. But here, in a wearable system, this solar cell, integration of solar cell and all other supercapacitor or sensor become a bulky one. So we are now pointing towards a miniaturized energy store energy generator called a triboelectric. I hope all of you know how to work, how a triboelectric nanogenerator works. So in a tribo, as compared to a piezoelectric material, in a triboelectric contain two dissimilar substrates. And in which these two dissimilar substrate, we have one electrode is conducted on the top and one bottom, and one electrode conducted on the deposited on the top. And when these two dissimilar material contact between, due to triboelectrification or friction, and opposite charges are created on the surface. And when a small force is applying to separate this, and electrons flows across the electrode to provide a potential difference between the device. And this energy can be generated by using any ambient motion like motion from tidal energy, heart rate, sound wave, wind power, human motion. Recently, one of the work reported that they used a energy generator by using rainfall. A solar cell integrated with a triboelectric nanogenerator, the energy generated from using a rainfall. So a triboelectric nanogenerator can be generated by using any ambient motion. So one of the major problem of this triboelectric nanogenerator is that material. We can see that there is a two dissimilar material. This dissimilar material have different dielectric permittivity or thickness. So when this electric field generator and this electric field propagation required a particular dielectric material, and its thickness is very much important. As you can see from the first figure that triboelectric layer 1 and triboelectric layer 2, there are different substrate and different electrodes are used. And this triboelectric layer 1 Total capacitance is depends on the capacitance of the PDMS, one of the contact surface which is required for high surface roughness material, and also a capacitor from the substrate. And then total permittivity of this layer is depends on the relative dielectric permittivity of the PDMS or the substrate, and also the thickness of the total thickness of this one. So for a simulation application, what our student used that different substrate we used PTFE, PET, paper and backlight, and by using different relative dielectric constant. And then during the simulation, we varied the distance. Distance, you can see the distance in nanometer range, the thickness of this, and also we varied the different substrate materials and also the thickness of the dielectric. By varying the different substrate, you can see here PTFE, PET, paper, and backlight. You can see how the output voltage generated by using the different substrate. From this, we observed that when we using a PTFE with a relatively low dielectric constant. From the previous table, we observed that a PTFE have a relatively low dielectric constant have generated high voltage. And also by varying the thickness of the substrate, you can see from the next figure, when a low thickness of the substrate, for example, 1 micrometer thickness, we observed a high voltage generated. From here, you can see the charge density, how when the different permittivity material, different material are using, how the charge density is generated, and also how the output current density is generating. You can see in conclusion here, you can see that when the relative dielectric constant is varying, how the output voltage is varying. So from the PTFE to PVDF, you can see PTFE shows very high very high voltage generation when relative dielectric constant is very low. As similar, when we using different this material, we observed that a short circuit current density or a charge density are almost same nature. However, when we are using different thickness of the substrate, you can see when the thickness of the substrate is very low, it generates high voltage, and when the thickness is when the thickness of when the thickness of the material is very low, the current density or charge density is also very. In optimizing this, our simulation results, what we are planning to do that we are fabricating based on this simulation result. We are planning to fabricate a new triboelectric nanogenerator, and from the present result, you can see that a PTFE based device shows very high output voltage with a low thickness, and then integrate this with a wearable supercapacitor, which I already developed now, and we are now doing this fabrication. My student is doing this fabrication of this triboelectric, and even my team members, Professor Ravinder, Dahiya, our supervisor, and our colleagues, and the supporting funding agencies from the university. Thank you.